and that is the first things first. The first sections we study this particular type of the force, and this is the first kind. And again, in these chapters, we still study single degree of freedom, forced vibrations, and right now the force type. In chapter 4, we talk about extending to many types and not limited to simple harmonic. And the first type we still is the general concept of the harmonic force. However, this harmonic is contains multiple frequencies. Okay, for example, you look at this context here. Basically, this force is containing a constant and also combinations of the harmonic terms, and this harmonic can be from omega, for example, omega t, 2 omega t, 3 omega t, 4 omega t, etc., etc. Okay, so basically this is containing in infinite numbers of the individual harmonic terms, and for this case, and because this system is linear, so the whole response of the steady-state response of X can be the summations of the response to individual terms. Okay, so again, right now I'm talking is the key concepts. The steady-state response of the systems can be a combinations of the response to individual terms. Okay. And take summation. So in here we can utilize the way we have. This is not useful. Let me put aside. Here, let me write it up. Our template. The template is from previous chapters. So in chapter 3, when we deal with such a systems. And for example, F now and cosine omega t. Okay. And we know that for this response, the steady-state response. Okay, that means the steady-state response. And we know we have this template. Anyone can write it without referring to any textbook or note? Okay. Yeah, okay. I heard about that, something the square root. Sometimes you square summation and KCM, right?
Is it EST on top?
Okay.
They're responsive to top.
Okay. Good.
That's not overstated.
Good. Okay. Good. How do I write it? There's so many forms, right? Okay, so I assume everyone got it. And then you write one of them. Okay, that'll be this one. Right, so this is one of them. Right. And the other form, and let me try, will be delta ST. Okay. So this is our template. So let me box it. This template, basically, you can see that is a response to one term of harmonic, and that harmonic function basically is only have one frequency. And right now we look at here for our systems here in chapter 4, and I would say the first type of the functions is this one. So here we have is n x double dot plus cx dot plus kx equal to, for these general terms, and let me expand it in the vertical way. So the first term is a now divided by 2 plus the second term is say a1 cosine And when j equal to 1, so basically that is a1 and cosine omega t. The second term is b1 sine omega t. Then we continue. So the follow-up is a2 cosine 2 omega t plus etc. Okay, so we repeat it. And so right now I want to tabulate. So you can see the response. Right now I on the right hand side, compared to our template, I decompose the total force into individual terms. Each term actually taking up the same template. For example, for this term, you might imagine this term is equal to cosine and 0 times omega t. Okay, so that is a 0. Be good? Okay. So in this way, let me write it up the response of the x to individual harmonic term. I write it up here. So that response follow up this template. XST will be equal to, depends on which form you like. Actually, I like to take this one because this is less writing, but let me take this one, okay? Take both. So for this one, what is F now? F now, compared to that one, that is the magnitude of the harmonic force. So taking out that information, the magnitude of the harmonic force for this term is A0 divided by 2, right? Good? Okay, and then we write it up continuously. That is K minus M times omega squared. And omega here is 0. So times 0 squared plus C omega squared. This one, omega equal to 0. So basically the 0 squared. Be good? Okay, so for this case, if you like, you can take the delta ST. What is delta ST? Delta ST equal to F now divided by K. So basically here is F now divided by 2 and divided by K. So that is delta ST. And for this case, R equal to 0. So let me label it. And R equal to working frequency divided by natural frequency. For this case, is 0. So that is basically that is equal to 1. Okay, so that is corresponding to this one. I need to give myself more space. So let me move this term a little bit lower here, and then plus A1 cosine omega t. Okay, so now I work on this one, and then plus continue. So corresponding to this one, the response is XST. So right now I'm doing the linear decompositions of the system response to individual terms, and then I will take summations. So this one again, compared to this template, F now is the magnitude of the harmonic. That is A1. Okay, and then K minus M times working frequency square, and here is omega plus C times working frequency square. Okay, so for this case, here R defined by omega divided by omega n. So that will be equal to delta ST, and that is the A1 divided by K. Because delta ST by definition is the magnitude of the harmonic force divided by spring constant. The magnitude of the harmonic force is A1 for this term. Okay, so we continue, and here is B1 sine omega t. Sorry, let me emphasize here. This is the time response, and here I write is a magnitude only. Okay, and you know the whole thing. Sorry, I made a kind of the. Suppose this one also must be multiplied with cosine omega t. t minus some kind of the phase angle, whatever, right? So here I emphasize it's on the magnitude. So why not here I added up the magnitude. I don't know whether you still have a space in writing your notes, or we kind of start from scratch, from the beginning. How to do it?
I have space.
You have space, okay. So why not you try to find me? I don't want to rewrite. So here would be times cosine omega t minus phi. Okay, so here I can write it out the phi. Let me write it up here. And the phi equal to arctangent c omega k minus m omega square. Okay. The phi is the phase angle. So this is a complete description. So magnitude multiplied with cosine, and then the cosine follow up this pattern here. Okay. So basically here I will add it up. This one multiply with cosine and omega t minus phi, and then we have the phi plug into that formula again. For this case, the omega equal to 0. Okay. So that means here I multiply with cosine omega t minus phi. Sorry. Okay. So for here, this one is times cosine. Before I move on here, this is the working frequency, right? And here the omega, this term is the working frequency, and here for this case, the working frequency equal to 0. So here you can see the omega equal to 0. Can you see it? Okay, so now this is the forcing term, so omega t, we follow that one minus phi. Okay, so here the phi equal to arctangents, and then follow up that pattern c omega and k minus n omega square. Okay, so in this way I drop this term for space. So now for sine, then basically here is x as t equal to, again, that is sine. So this is our frequencies, the harmonic functions. So the steady state must follow the same patterns, sine, okay, and omega t, and simply follow the same pattern of a harmonic function, but with the certain phase angle delay. So we have this one. So the same thing, the phi equal to the same patterns we have arctangent and c omega k minus c omega m omega squared. And this one the same thing, the magnitude with the same magnitude here, so that is B1 and with the same the denominators. Okay, so basically A1 cosine, B1 sine, they have the same template. They have the same phase angle, but simply have the sine, cosine individually. Be good? Okay, so then we continue to work on other terms, say A2 cosine 2 omega t. So right now for this term, this is our working frequencies. So for the template, you plug in working frequency as 2 omega. So let me write it up here. The steady state will be equal to the magnitude, and then cosine. Let me write up the whole pattern first. And the function, harmonic function is 2 omega t, so we follow the same patterns. And then we have a phase angle delay. Okay, so here the phi will be equal to, okay, then we can build up the templates first, the sequence. Okay, so that's the things. So we follow up the template. The template saying that the numerator is the magnitude of the harmonic functions, and which is A2 here. So we put an A2 here. Okay. Then denominators here, a little bit careful. We follow up the template. That means the spring constant, and spring constant is given, and minus m. M is the mass, is given. Okay, now come to the here, m times working frequency square. You have to know the meaning of the parameters or variable in the template in the formula. This omega representing is the working frequency. Okay, so for that case, this parameter must be replaced by the corresponding working frequency. For this case, is 2 omega. So that means n times working frequency for this case become 2, 4. Let me write it up here. N times 4 omega squared. We good? So right now, this representing again is the working frequency. So we plug in the working frequency, which is 2 omega, into this point right here. So that becomes 4 omega squared. We good? Okay, and then plus C times working frequency. So C times 2 omega, so that becomes C times 2 omega squared. We good? Okay. So now for this one, again, for the phase angle, the numerator equal to C times working frequency. So that means C times 2 omega basically to C omega. So this is K times 4 n omega squared. You good? Okay, so in this way, in the similar, if we keep plugging, say, sine 2 omega t, so again, for this term, you should be able to write it up in similar form, so that the SST will have the same things, and here is 2 omega t minus phi. So here we simply take sine. Here is B2 here. You good? Okay, so you can keep practicing. So say if you want to continue, you continue. Okay. So basically here, if we take summations together, so whatever the response to how many terms, so here our steady state response of the systems will be the steady state response of the, you simply take the summations of the whole terms together. That is the total response to the original systems and corresponding to this one. Okay, good. So basically here I would say for the first portion, for the first type of the force, that is a combination of the harmonic functions, and basically we simply utilize our chapter 3. So in this section, I don't think everything is spatial and everything is we have known. And the only thing new to everyone is this. The linear system allows us to do the decomposition superpositions. So here, this is the way we're using the linear decomposition to decompose the linear response into individual terms we already know. And here we take the superposition of the individual response, then that go back to the total response of the system. Okay? And so in this way, I would say this section, this one, can be extended to many types. If you remember what we have learned in chapter 3, and we based upon this, we studied the phase excitations, Okay. So, for example, if the base excitation right now you're preparing for the test, coming test is the base excitation is one simple harmonic form. But in reality, the base can be such a case. So think about, right now would be a good time when you prepare for the test, you might extend your thinking toward this. Okay, that's the first one. The second one, the base excitation can be extended to, say, vibration picks up, which means the design of the vibrometers, design of the accelerometers. And right now you have practiced is the accelerometers and vibrometers response to single harmonic term. But in general, that single harmonic term can be extended to such case. So everything you learned so far should be able to extend into this kind of linear decomposition superpositions. Okay. So whatever we have learned in chapter 3, we can extend it to here. Okay, and that is a huge topic, and that kind of gave me a lot of the space I can design the various type of the homeworks. Okay, and or for the test 3, the next one. Okay, so. So here, the finding this one, that basically gives us the okay, and on the other side, this is the very traditional time. This is the template. If you remember, the template here is what we got from directly solving the differential equations. And on the other side, these slides are using the transfer function concept and to explain the same story here. Okay, and let me explain the things on the other side, and we can compare. So in this way, to allow me to utilize the space, let me turn off this for a while. The doctrine, we can have a new section. Okay.